Section 3.1, we're going to study two exercises that are slightly harder. The first one we want to look at is exercise 95. Find the derivatives from the left and from the right at x equals 1 if they exist. Is the function differentiable at x equals 1? So the function we are given is a piecewise function, f of x equals x minus 1 cubed if x is less than or equal to 1, and f of x equals x minus 1 squared if x is greater than 1. If we don't know what to do, we might as well start by sketching a graph. So the first rule, x minus 1 cube, is valid if x is less than or equal to 1. And what is this? It's a cubic function. It's actually the parent function that has been translated one unit to the right. If you don't know transformations well, you can still make a table of value and find some values for that function. So I know that it's going to look like that, as if it was a cubic function going up like this, but of course we stop at x equals 1. And then on the right side, the second rule is f of x equals x minus 1 squared. Once again, this is just a parent function translated one unit to the right. It's a square function, so it's a parabola like this. Okay, on my graph it looks like there's kind of a symmetry here, but this is a cubic and this is a parabola, so it's not quite the same curve. The question we have to answer is, what is this slope as I approach x equals 1 from the left, and then what is the slope as I approach x equals 1 from the right? And then if these two are equal, then we will be able to say that yes, f is differentiable at x equals 1. So to figure these one-sided derivatives, we need to use the alternate definition. We're going to look for, this is x equals 1, the limit as x approaches 1 from the left. So in general, let me just first write what it is. As x approaches a value c from the left, it's the quotient f of x minus f of c over x minus c. And then we would need to do the same, but with a little plus here, with the same formula. So in this case, we're focused on c equals 1. So the limit as x approaches 1 from the left is f of x minus f of 1 over x minus 1. F of x, since we are on the left of 1, we need to use the first rule, so it's x minus 1 cubed, minus, what is f of 1? Well, let's be careful. When x equals 1, we have to follow this rule. I'm going to plug in 1 here, and 1 minus 1 cubed is 0 over x minus 1. Oops, I forgot, as always, to put the limits. It's okay to forget, but you need to realize you forgot and then add it everywhere. If you don't put the limit, then it's really something different. So it's wrong. Equals the limit as x approaches 1 from the left. First, we need to clean this up as much as we can, and it's great. We can cancel out x minus 1. So it's the limit as x approaches 1 from the left of x minus 1 squared. And now I don't have an issue if I plug in x equals 1, which I do. I had an issue earlier because it would have been divided by 0. But now I can plug in x equals 1. 1 minus 1 squared, 0. What does that mean? It means that the slope here as I approach from this side, the slope is 0. The question is, will I have the same slope if I approach from that side? If I do, then they connect smoothly. If I don't, then there's some kind of sharp turn. You know that a parabola has a slope of 0 here because the parabola actually is symmetrical like that. But we're going to do it algebraically. So the limit as x approaches 1 from the positive side is also the same quotient. But this time, since we are for taking values of 1 that are above 1, we need to follow the second rule. So it's x minus 1 squared minus, what is f of 1? Well, f of 1, we're looking at x equals 1, so we should actually plug it in the first equation. It doesn't matter this time, but it may matter sometimes. So anyway, if I plug in x equals 1, I get f of 1 equals 0 divided by x minus 1. Guess what? I forgot to write the limit. Equals limit as x approaches 1 from the right of x minus 1 squared over x minus 1. Beautiful, it cancels out. Limit as x approaches 1 of x minus 1. Now I don't have a division by 0, so I can plug x equals 1 in, and I get 0. So we get a confirmation that the slope when I approach from the right is also 0. So 0 from the left, 0 from the right. I found my two one-sided derivative, and I can also answer yes, the derivative exists at x equals 1. Actually, I can even write it, f prime of 1 equals 0. One additional note, if you were to write the derivative f prime of x as a piecewise function, we will see how to get that much more easily in the next section, but I want to address this issue already. The derivative of x minus 1 cubed is 3 times x minus 1 squared. The derivative of x minus 1 squared is 2 times x minus 1. And you can say that this is true for these values. Had we found that the derivative was non-existent at x equals 1, we should be careful and not put this equal sign here. This is a very tiny hidden detail, but it comes up once in a while in AP calculus exams that they trick you, and you have to be careful not to put the 1, because actually at x equals 1 the derivative does not exist. Okay, so that was the first exercise. Second exercise is problem 97. Determine whether the function is differentiable at x equals 2. It's no different than the exercise we just did. F of x equals x squared plus 1 for x less than or equal to 2, and f of x equals 4x minus 3 if x is greater than 2. So what I didn't mention in the first exercise, because it was pretty obvious, is that if we even wonder whether a function is differentiable, first of all, we need to make sure that it is continuous. So here, is this rule drawing a function that is going to connect with this rule? Yes or no? No. And to do that, we just plug in x equals 2 here, so we find that at x equals 2, I have a graph x squared plus 1, so at x equals 2 it's going to be equal to 5. This graph is a parabola. It looks somewhat like that maybe, and here we are at 5. Now if for some reason this line didn't start at f of 2 equals 5, if it didn't go through the point 2,5, then we could just stop right here and say, no, it's not differentiable. It's not even continuous. How can it be differentiable? So let's see, if I plug in x equals 2, I get 8 minus 3 equals 5. So yes, it looks like it connects. So it's a line for y equals 4x minus 3. I'll draw it like this. The question is, do I have the same slope when I approach from the left and from the right? So let's see, we're using the same alternate definition for the derivative. The limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2 equals the limit as x approaches 2 from the left. So when we are on the left, we are following this rule, x squared plus 1 minus, what is f of 2? We calculated it, f of 2 equals 5 over x minus 2, which is the limit as x approaches 2 from the left of x squared minus 4, which is the limit as x approaches 2 from the left. X squared minus 4 is x plus 2 times x minus 2, so I'm going to be able to cancel the x minus 2, which is wonderful because this fraction was my problem. I could not plug in x equals 2 in because it was creating a division by 0. Right now I can plug in x equals 2, so I get 4. So the slope when I approach from the left is equal to 4. If you remember lines, we know the slope of a line. We know that the slope of this line is this value here, ax plus b, or mx plus b. So actually, we could take a shortcut here, and feel free to do it, because this is a knowledge that we have. It's acquired knowledge. The slope of this line is 4. We don't even need to bother doing the limit. I will take the limit just for practice. So it's the same quotient, but this time I'm looking at values that are greater than 2, and therefore I need to say that f of x is 4x minus 3 minus f of 2. When x equals 2, it is this function here, so it's 5 over x minus 2, limit x approaches 2 from the right. This is the limit as x approaches 2 from the right of 4x minus 8 over x minus 2. Beautiful. I can see how it cancels out if I factor out a 4. So let me just jump right to the answer 4. So, conclusion, yes, it is differentiable at x equals 2. In fact, I can say f prime of 2 equals 4. Let me just check that I answered the question completely. Determine whether the function is differentiable at x equals 2. Okay, I did everything I needed, so I'm happy. All right, thank you.